Well, good afternoon, everybody. It's 1 minute after 1. Hope everybody had a good lunch and they're enjoying the conference so far. This is Scott Weissman, and I'm going to introduce our next keynote. Alex Carrier is an esteemed SHRUG volunteer who was helping us, along with others, come up with ideas for keynotes. And Alex said he had was invited to a webinar where our next speaker did a presentation. And this is Nick Rabinowitz I'm talking about. And Nick was presenting and talking about hexagons, H3 hexagons. And we met with Nick and we really liked what he had. So Nick is a senior staff software engineer at Foursquare, which is a tech company focused on location-based analytics and visualizations. Before he was at Foursquare, Nick helped create the H3 hexagons that he'll be talking about today, and he developed these while working at Uber. His work covers a broad range of topics, including data analysis, disaster response systems, user research, and visualization, which build on over 15 years of experience working with web technologies. With that, I'm going to hand it over to Nick, and Nick will go further and tell a little something about himself and tell us about the hexagons. Thank you, Nick. And I did want to mention real quick, questions. If anybody has questions, I'm sure there'll be a lot of them. Use the questions pane, the section in your GoTo dialog. Go ahead and put those in at any time that you have the question, but we will be taking those questions to Nick at the end. Thank you. Go ahead, Nick.
Great, thanks so much for the intro. Hi, I'm Nick, and I'm here to talk about your friend, the hexagon, and how to do geospatial analytics using the H3 discrete global grid system. So very quickly about me, Scott said most of it. I'm a senior staff engineer at Foursquare. I've worked at Unfolded, which is a startup focused on geospatial visualization. Before that, I worked for many years at Uber, some other startups, some nonprofits and NGOs. I've been, every time I look at this slide, I have to update. I'm pushing 25 years now as a software engineer, I'm sad to say, or perhaps thrilled to say. And most of that time has been spent recently working on mapping and data visualization. For the last 4 years approximately, I've been the core maintainer of H3.js and one of the core maintainers of the H3 library that I'm going to talk about today. And I like to say that I'm secretly an English major. It gets a little less secret every time I say it, but you know, it didn't start with a CS background. I came to it naturally because it was filled with things I loved. I also wanted to share this as a different kind of introduction. This is something that my kids made yesterday and really just got right to the point. This is my Pokemon card, Datamon. And as it notes, one of my attacks is to say code stuff, and I say so much code stuff that it deals damage, so consider yourself warned. So a quick outline of what I'll talk about today. I'm going to give the intro that I just gave. I'm going to talk a bit about global grid systems and how they might fit into geospatial analytics and GIS systems. I'll talk specifically about the H3 library, which is this hexagon-based global grid system that we developed at Uber and which is open source and something I continue to work on to this day. And I'll go through some examples of how to use H3 in practice. So what are some of the things you can actually do? What does it look like to do analytics with a discrete global grid system? And then at the end, we'll have time at the end for Q&A. So please hold questions until the end, but please feel free to put them into the questions for the webinar now, and they'll be queued up for when we get to Q&A. So what is a geographic grid system? This is something some of you may be familiar with already. Some of you may have never used a grid system. The basic premise here is that the real world is an incredibly messy place, and we all know this. Anyone who's dealt with geographic data in any way, we've seen all the ways that our geographic data, fails to represent the real world. in meaningful ways. Nothing in the real world has a hard edge. Nothing has a perfect location. Nothing has, a fixed location. Everything moves around in different times and different parts of a city. Sometimes you're trying to map that movement. Sometimes you're trying to keep things stable. But in general, we're all constantly dealing with these very hard to model things in the real world whenever we're making maps. Maps take all these things and they put it into these abstractions that we can more easily work with. We're all familiar with them, points and lines and polygons. These are the things that we work with as our units of analysis on a daily basis, but they're still pretty messy. If you look at a map that has a lot of features, the polygons have many different edge cases. The points are not exactly where the things they're modeling should be. The lines are a poor approximation of what a road actually looks like. And you end up with, a pretty complicated set of features, especially if you want to do anything mathematical, any real kinds of analysis. You have to do a lot of work to get these things to work together. So a geographic grid system tries to address some of this mess by putting it all into this neat mathematical space. And it applies this abstraction of uniform cells. So basically it splits up the entire world into nearly equal cells of the same size, same shape, roughly equal area, and that allows you to put all of your data into one unit of analysis. So the real world is messy, but your new unit of analysis is super clean, and you can do all sorts of things with it that are harder to do with traditional data. One of the great things about these cells is that they are unbiased by what's actually going on in the world. So they're unbiased by the natural features of the world. You don't have big interrupts where you have a river or a lake or an ocean. And they're unbiased by human processes like zoning regulations or administrative boundaries, which can really skew some types of analysis. And there's a wide range of algorithms that you can do on a grid system that would be difficult to do with traditional geographic data. And a lot of the reasons why I've worked with grid systems in the past is to run the kind of algorithms and do the kinds of analysis that would be very hard to do with a set of polygons or a set of points. People often ask how these, how are these different? Why would you use a grid system instead of using, say, administrative boundaries or, your own binning system that perhaps your GIS software can provide? For administrative boundaries, the biggest difference is that most administrative boundaries are in some ways an artifact of history. I like to think of them as being an artifact of someone else's use case. Those use cases might be political. They might be, in the case of something like neighborhoods, maybe they're a real estate use case, maybe they're a zoning use case. And sometimes those use cases are really important to you. Sometimes you really care about the different zoning laws in a particular parcel A versus parcel B. But sometimes you don't. And when you don't really want to use those areas in a way that that requires you to care about those things. You want to have an unbiased set of areas that you can use for binning and analysis. Ad hoc bins, something you can usually get in a lot of GIS software. You can make your own hexagon bins, you can make your own square bins, and these things do give you this, relatively unbiased shape and, a sort of common unit, but it's a unit that's very specific to your own analysis. Where geographic grid systems really shine is when you want to bring lots of things together. You want to use stuff from system A and system B, and especially if you're working in a situation where you're making systems that need to interoperate, having a grid system that's shared gives all of the data a common unit of analysis, and allows you to do a lot of easy joins. You have this one identifier for every grid cell that's easy to share across systems. That's very hard to do with an ad hoc bin. Essentially, if you try to use this ad hoc bin for joins across systems, you're basically making your own discrete grid system in a way that probably doesn't match those that have already been built. So I've talked about grids. A grid system usually has multiple grids. So not only are you covering the entire world with equal area cells, you're usually developing a hierarchy of grids from large to small. And sometimes these grids have a specific hierarchical relationship, sometimes they don't. In the case of H3 and many other grid systems, you have a parent cell that contains a set number of child cells, and then that repeats downward throughout the grid system. So how would you go about building a grid system? There are a few choices you need to make. And most of these choices are essentially orthogonal, so you can choose them, without regard for each other. But there are some overlaps and some constraints that one choice will put on you. So the first thing is to choose a base polyhedron. And I say a polyhedron because while you can use, a cylindrical projection as the basis of a grid system, most people doing discrete global grids don't. And that's partly because it's not uniform across the world in any meaningful way. If you're using, a cylindrical projection, you end up with singularities at the poles. You end up with, it's very difficult to deal with everywhere across the world in the same way. A polyhedron is a model that's commonly used for this kind of system, where you take one of these Platonic solids. These are the only Platonic solids the only solids that have one shape to every face. You can lay this over the world, and this gives you as many projection surfaces as you have faces on your polyhedron. So there are different reasons why you might choose these different polyhedra, but most grid systems start with one of these and then build their grids on top of each face. Once you have a polyhedron, you need to orient it relative to the Earth. So you can align it with the poles, you can align it with the equator, or you can make different choices. And we'll talk a little bit more about that later. And then you take each face of the polyhedron and you split it into uniform cells. And those uniform cells are going to be some shape. And we'll talk a lot about why some shapes might be better than others. Obviously, I think I've already given it away that I have a preference for hexagons on this, but there are other choices that you could use. You project those cells onto the Earth's surface. So basically each of these polyhedron faces gives you a new projection plane you can use to project your Cartesian grid onto the Earth's spherical or ellipsoidal surface. And then you choose an indexing system. So you want every cell to have a unique identifier. Ideally, you want that identifier to be quick to calculate and easy to understand. And so you need some way to uniquely identify every cell in your grid system. There are a lot of example grid systems out there. The simplest is just the graticule, the lines of latitude and longitude, which you can use as a grid system. You cut a few decimal places off and you've created a new grid cell. Web Mercator tiles, this is a pseudo grid system that's commonly used in a lot of web-based systems, where you have a unique addressing scheme for different areas of the world that can zoom in and out, and you can base your tile sets on this. This was first popularized, I think, by Google Maps and maybe Bing Maps as well, to basically split up the world into pre-rendered tiles. More recently, you have S2, which was a Google system, which uses a quadrilateral grid cell, and has some interesting ideas about how to index the world, which allows you to do sort of range queries for nearby cells. And most recently, you have H3, which is this system that we built at Uber using hexagonal cells that splits the world up in this way and uses a different kind of mechanism for indexing. So the most common question that people ask is, why would you use hexagons? Squares and quadrilaterals are much more easily comprehensible in some ways. We're all a bit more familiar with them. And they're easy to subdivide, but hexagons give you a bunch of unique advantages when you're creating a discrete global grid. So there are many different shapes you could use to tile the plane. In this case, we have fish and birds. Why are we using hexagons or squares instead of fish or birds? This is sort of a reductio ad absurdum. This would obviously be impractical for a discrete global grid system, but why? What makes it bad, and what makes another shape good? So these are some of the things that we care about, and these are sort of generic considerations. You may choose to really care about one or the other of these depending on what your use case is. But these are things that we care about when we're trying to create a grid system that's going to work for many, many use cases. The first one is that we almost always want our cells to have uniform shape. We want every single cell to be the same shape. And we would like to have, so that right away, that cuts out the birds and the fish because you have two shapes there. You want to just have one shape so that you can treat everything equally. Ideally, you want that shape to have uniform edge length and uniform angles. So that's bringing us into the regular polygons. That cuts out anything that's not a regular polygon. And as you're probably aware, there are only 3 regular polygons that you can use to tile the plane. So already we've cut our choice down to 3 options. You've got your triangles, you've got your squares, and you've got your hexagons. You ideally want your shape to be optimally compact. And one way of thinking about this is to say that you want the points, any point that falls within that shape, you want it as close to the center as possible. So this sort of shows you how this might work out on some of the different polygons. And you can see right away that hexagons are actually a little bit better at being optimally compact than these other shapes. The difference between the farthest vertex and the farthest non-vertex, the farthest in radius, is very small compared to a square, especially compared to a triangle, where the in radius is really short and the radius to the vertex is very long. And you can see that the hexagons are this very efficient way of storing points. This is part of the reason why hexagons come up so often in nature, because they're this optimally compact shape, and it works out really well if you're, for example, a bee. You want them to be optimally space filling. So one way to think of this is for all the sets of arbitrary polygons that you might want to map to a set of cells, which tile is going to be best at fitting the most area possible of that shape, of getting as close as possible to the original polygon. And again, hexagons win out here. And I don't have a mathematical proof for this, but I do think that in general, it's been proven that hexagons are very good at fitting these shapes. Obviously, triangles would be potentially better. You could break any hexagon into triangles, and therefore you should be able to fit anything you can fit into hexagons, you can fit into smaller triangles. But if you're comparing equal area cells, hexagons generally win out. They can represent a wide variety of polygons with a pretty high level of accuracy. One of the other things you care about, and this matters a lot for certain types of algorithms, and this is probably the thing when we were first developing H3, this is probably the thing we cared about the most, is uniform adjacency, which is about how close you are to your neighboring cells. And you can see that for something like a square, you have 2 classes of neighbors. You have the neighbors who are adjacent on an edge, really close to you, and you have the neighbors who are sort of adjacent at a corner and who need to be treated as neighbors, but as some special secondary class of neighbors. They're not really the same as your near neighbors. Triangles are even worse. You actually have a bunch of different classes of corner, vertex adjacent cells, and it becomes very difficult to do any kind of algorithm where you care about traversing from one cell to its neighbors because you no longer know exactly what a neighbor is. As you can see, the hexagons win out big here. Every neighbor is equal. And so if you're doing something, for example, like a smoothing operation where you want to spread out some data across all of the neighbors, you can do that very easily. You can do a blur operation. You can do the kinds of things where you're looking around a particular cell to see if points exist in its neighbors, doing essentially a low-cost radius search. You can do that very easily with hexagons. And so uniform adjacency is a really good property to have for a grid cell. You also want hierarchical relationships. And the reason for this is, as I was saying, most grid systems have multiple levels that exist in some kind of hierarchy. And so you want to be able to subdivide one cell into its children and its grandchildren and its other descendants. This allows for good indexing systems. It allows you to aggregate upwards when doing different kinds of binning or data analysis. And it's a really useful property. Hexagons can work here, but you can see that they're a little bit worse than triangles and squares. Triangles and squares you can subdivide perfectly into the same shape at a smaller resolution, whereas hexagons you can subdivide imperfectly. This is the subdivision. There are different kinds of ways that you can move down to a finer resolution for hexagons. This is the subdivision we use in H3, where you subdivide into 7 hexagons that are nearly represent the parent hexagon. And the good thing here is that while you have a margin of error, it's a fixed margin of error. And that margin of error is the same across the grid. It's also the same even if you're subdividing into grandchildren or great-grandchildren. But it's not quite as good as a square cell offers. And finally, you want low shape distortion and you want low area distortion. And as anyone who's dealt with projection system knows, these are usually a function of the projection you're using. And the projection, how much distortion you have in your projection is often a function of how large your projection surface is. If you're trying to project a very small area of the world, you can have very low shape and area distortion. If you're trying to project the entire globe, then often you have much larger distortion, regardless of the projection you use. So I show the polyhedra here because one of the big considerations here is how many projection surfaces do you have and how large are they? The more projection surfaces you have, the smaller they are, and the more accurate your projections can be. So you can see we go from basically 1 projection surface in the cylindrical option over to 20 for the icosahedron. The icosahedron is probably the best option if you can use it. The limitation there is that you can't subdivide the faces of an icosahedron into squares. You can only subdivide them into triangles, or as we'll see, into hexagons. And conversely, if you have a cube, you can basically only subdivide it into triangles or squares. You can't use hexagons at all. So the polyhedron choice is in fact closely linked to which cell shape you end up using, because it has different implications for which cells are actually available for your grid system. So if we look at a square, which we're all familiar with and is probably what most of us think of when we think of a grid, it gives you uniform shape, uniform edge length, uniform angles. That's great. It gives you really good hierarchical relationships with perfect child containment. That's great. But it misses out on a lot of these other things that we care about a lot when we're doing analysis. By contrast, hexagons give you almost all of these things except for perfect child containment and except for uniform shape. I'll come back to that one in a second. We can almost tile the globe with hexagons, but not quite. And so sometimes you have to deal with pentagons as well. Most of the time you can ignore that, and that makes it makes us able to skirt this uniform shape issue a little bit. So these are many of the reasons why, when we were designing the H3 system, we decided that hexagons were going to be a better generic cell than squares. This might not be true for your use case. So if you really care about perfect child containment because you want to do perfect aggregation, for example, then a square grid system might work better for you. But for a general purpose system serving many different use cases, hexagons are actually a great fit. Another thing you might care about is whether or not they're cool looking. And I hear a lot of maybe slightly dismissive comments saying that, the main thing about hexagons is they look cool. And well, first of all, I think they do look cool. But second of all, I think that they look cool because they are cool, because our brains have this amazing visual processing power. Anyone who's worked in data visualization or cartography knows that it's really amazing how much data we can process through our eyes very, very quickly. And I think that part of the reason why a hexagon map is going to look better than a quadrilateral map is that it actually is a better representation of the real area that we're working with. And we can see that very quickly. We can see that this looks like a cleaner surface on the right. So this map on the right is a hexagon map of trees in San Francisco. The map on the left is an S2 based quadrilateral grid showing the same data. And I think we can see very quickly that not only does it look cooler in quotes, but it's actually a better representation of the data that we're trying to map. And so that's one thing I would say is that, part of the reason you might choose hexagons, it's not just that they, quote unquote, look cool. It's that looking cool is actually a good proxy for being a good representation, a visual representation of the data you're trying to work with. So given all that background, that was a lot of in-depth hexagon talk, I wanted to get into the H3 library. The H3 library is a system that I helped to develop along with other engineers at Uber, and it provides a global grid based around hexagons. So going back to the choices you might need to make when you're constructing a global grid system, we chose the icosahedron for the base polyhedron. This is the best polyhedron available because it has the most projection surfaces and they're small, and so you can get pretty good, roughly equal area, low distortion projections. We use the Dymaxion orientation. So this is something developed by Buckminster Fuller. For a long time, it was the only orientation of the icosahedron that had been discovered that had all the vertexes in water. And so especially, you can see a little bit of bias coming from Uber's use cases here. Uber doesn't really care that much about water. It's a transportation company working mostly on land. And so not having to deal with these vertexes is a really useful property because you have some special cases of the vertexes that we don't really want to deal with. And so putting them on water means you can mostly ignore them in many types of analysis, unless you're doing analysis that needs to work with water area as well as land area. For the uniform cells, we chose hexagons for all the reasons I just covered. We use a mnemonic projection. The main reason I think we chose the mnemonic projection is that it means that when you go from this Cartesian hexagon grid to the projected grid, all of our lines end up being great arcs. And that's a useful property to have in a grid cell. It gives you some confidence about the way that the edges of the grid cell work. The other reason is that mnemonic projection is fairly fast. And one of the things that we cared about a lot in H3 was performance. How fast can we do analyses that cover the entire world, for example. And finally, and I'll talk more about this in detail in a little bit, we used a hierarchical addressing system to create the index. So you can see that basically you have a parent and its children and its children and its children, and you're basically walking down that hierarchy and saying, I'm in, parent A, child 1, grandchild 3, great-grandchild 4, etc. So this sort of shows you a little bit about how we constructed the grid. We took the icosahedron, projected it onto the surface of the Earth. We put our base cells, the largest possible cells in the grid system, get projected onto each face of the icosahedron. And you can see that you have 4 hexagons on each face, and you have 3 half hexagons that are complemented by the other adjacent faces. And then you have these little bits that end up being pentagons. And I'll talk about those in a sec. And then for every cell in your grid system, starting with these large base cells, you subdivide and subdivide and subdivide. And so we go down for 16 resolutions. You start off with these base cells that are maybe the size of a small continent, and you end up with the finest cells that are under a square meter. So this gives you an ability to address almost anything you want to address in the world at a precision that you can choose. So talking very briefly about the pentagons, mathematically, it's not possible to tile a sphere only with hexagons. If you're using an icosahedron, you can see when the vertex comes together, you have 5 faces of the icosahedron coming together, and you end up with a pentagon. So we do have to deal with pentagons. There are 12 at every resolution. The good thing about this is as your resolutions get finer, your pentagons are very few and far between. If you have millions of cells at a particular resolution, you still only have 12 pentagons. And the way we usually treat the pentagons is essentially like a kind of, mediocre hexagon. It's a hexagon that's missing one part, one axial direction. And you can use that kind of abstraction saying, oh, this is basically just a hexagon. to include them in most types of analyses that you would do over hexagons. I will say that when I look at the code in the library, an amazing amount of code in the library is dedicated to making sure that we handle the pentagon cases. One of the things I like about grid systems is that when you talk about edge cases and corner cases, it's very literal. Everything here is different at the edge, different at the corners. And pentagons are the extreme case of this, where the vertexes of the icosahedron have these special cases that you have to handle separately. So this gives us this H3 global grid. This shows you a couple of different resolutions of it and how it lays out more or less over the world. You can see that there are a few pentagons shown here, but that primarily we're dealing with a hexagon grid. And what we use to address cells within that grid is the H3 index. So I mentioned that this is a hierarchical index. You can imagine that for every cell that subdivides into 7 children, we can number those 7 children. These are actually the numbers we use, which is why they don't go in order. They're based on axial directions. But you can see that every one of my 7 children has a number. And so my address is basically just walking down to the finest resolution available for my particular cell and getting the different numbers. This cell might be, the cell labeled 4 here is the child of cell 0 above. And you can subdivide and subdivide until you get to the place that you want to stop the resolution that you care about. The way we've done this from a practical matter is to stuff all of these things into a 64-bit integer. This is a useful thing, a useful property for an index, because lots of data systems can store this as a single value. Lots of database systems can store it. Lots of languages can deal directly with it. The canonical form of the index is usually a hexadecimal string, like you see above here, the one starting 852. But the underlying form are these bits. And this is actually from a notebook I put together that you can find online that shows you what every bit means. So we have a few sort of housekeeping bits in the beginning of the index that tell you what kind of thing we're describing, maybe include some extra information depending on that kind of thing. We have the resolution. One nice thing here is that the resolution is human readable in the string index. So you can see this 5. Anything that, if you say 8.5, then you know that you're dealing with a resolution 5 cell. And then all the rest of it is this hierarchical indexing. I tell you what base cell it is, and then I tell you what's the level 1 number, what's the level 2 number, what's the level 3 number, and walk down until I get to these final bits that are just basically saying we no longer have data at this point. So we encode the resolution that we're actually caring about. And this gives us this very portable, useful identifier. It's really great to have a unique, easy to calculate identifier for an H3 cell, because it means that you can do all these things with these identifiers essentially as set operations. It's a lot simpler than dealing with a polygon representing the same area on the Earth. So I won't go into depth about the library itself. You can find out more at h3geo.org. But the key thing is it's open source. Anyone can use it. It has a fairly large user community. It's built in C. We built it in C for 2 reasons. One, because C code tends to be very, very fast. It uses a lot of low-level code where you can optimize things very well. And it also means that you can pretty easily create bindings for that in different languages. So we have sort of first-class bindings in Python and Java and JavaScript. We have a lot of community contributed bindings in other languages. So it's really easy to use H3 in your language of choice if you're a programmer. Python is probably one of the most commonly used, but I use JavaScript all the time. JavaScript is the one that I'm most familiar with. And one of the wonderful things about having it in JavaScript is that you can, if you're building a web application, which is the kind of thing I work on every day, you can do the same calculations in your server and in the browser. It makes it very easy to calculate H3 cells in the browser and to display them on web-based maps. And it gives you a lot of ability to do things either on the front end or the back end, depending on what's going to be fastest. In the application I work on right now, which is called Unfolded, I'll talk a little bit more about that later, but pretty much all the maps you see in this presentation came out of the Unfolded application. Using H3 in the browser allows us to do really fast, really responsive maps that can change as the user changes settings, rather than having to go back to the server every time and show you the spinning wheel that we all hate. And finally, there are extensions and user-defined functions for many databases, including Postgres, including BigQuery. These are mostly user-contributed, but they mean that you can actually use this right in your database system in many cases as a function you can use in a SQL query. Again, I won't go directly into every function that the library provides, but it's basically providing a lot of primitives for working with the grid, a lot of ways to transform from traditional data representations to grid-based data representations. The most obvious one here is indexing. I can take points and say what cell they belong in. I can take the cell and tell you what its center point is or what the boundary looks like. But also I can do things like take a polygon and tell you all the cells that are within it, or I can take a bunch of cells and tell you what the bounding polygon is for all of them. We also have a bunch of functions around traversal. So getting to the neighbors, finding a path between any two cells on the grid. And these allow you to do a lot of algorithms where traversal is important. And there's also a wide variety of utilities for inspection, ways to deal with edges. So we haven't had many use cases for this, but I think it's really interesting that you can also treat any grid as a graph of cells where every cell is connected to its neighbors. And so we have a concept of an edge, which is an alternative version of the H3 index that basically models those edges of your graph as individual units of analysis that you can use. So if you want to do flow analysis, for example, being able to have a directed edge representation that you can pass around in your code is very useful. So I wanted to go through a little bit of how H3 gets used in practice and go through a little sort of toy use case so you can see how it might actually work when you're using it in some sort of geographic analysis. And I started off here with a bunch of data from the Oakland Crime Watch data set. These are different places where crime occurred in the city. We might be looking at how crime changes across a given city, what geographic patterns we might look for. We might be interested in site selection. So if you're looking to, buy real estate, for example, you might want to know what the crime situation is in the place where you are purchasing a location. One of the reasons I like bringing this up is not because I think that crime is a big problem in Oakland. It is, but it's not perhaps as bad as everyone says. And that's actually the reason, is because usually when I see crime maps of Oakland or any other city, it just looks like, it sort of looks like a lot of measles. It looks like a lot of data points, and the overall impression is, wow, there's a lot of crime, rather than having a useful impression of what does this crime actually look like? How does it vary across the place where we're looking at? So the first thing that I usually do when I'm bringing point data into some sort of H3-based analysis is to index every row. So I look at every point and I find the H3 cell that it belongs to, the H3 cell that contains it, and usually I'm adding that as a row to my column rather to my data set. You can see here I've indexed every row at resolution 9. Once we have these bins, it's pretty easy to aggregate up. So in this case, I've just aggregated, here's the count of points in every one of these cells. As I mentioned, H3, like most grid systems, has multiple resolutions. You usually want to pick the resolution that's going to work best for you. The area is going to change. In H3's case, it changes by a factor of 7. So if we want more fine-grained data and a more fine-grained view, we might choose resolution 10 in this case. So this is a view of re-aggregating those same points into resolution 10. Now we have a more granular view of the overall distribution of crime within the city. One of the things we might do, we can, this previous view aggregates by count, but we can aggregate by whatever aggregation function we want. If you're dealing with categorical data, for example, the type of crime, you might want to aggregate by mode. That gives you the most frequent values in a particular cell. And you start to see some patterns here. So you see this brown area. I feel like this is mostly vandalism over here, whereas the orange area is actually, orange is more violent crimes. And so you can see that while there's a lot of crime over here, and there's a lot of crime over here, and they look pretty similar in this count view, when you start to look at the types of data, you get a different picture, and you can see that there's actually a very different kind of crime occurring over here than in the downtown area over here. I have these counts, but as we all know, frequently when you're dealing with human-generated data of some sort, in this case, incidents generated by people, it's often just a proxy for population. There's always, the joke that any map of frequency tends to start off looking exactly like a population map. So one of the things that we might want to do is to normalize by population, and H3 allows you to pretty easily bring in other data sets and bring them into your analysis and join them in a way that's really tractable for different kinds of calculations across data sets. So here's a population data set. This is a census population data set. What we've done here is to start with block group polygons. We find all the H3 indexes in each polygon, which is something that the library offers, the ability to tell you which indexes are within which polygon. And then we disaggregate the census counts. So, in some cases with H3, you're doing aggregation. In some cases, you're doing disaggregation. In this case, if you have a census block or block group that crosses multiple cells, you want to spread that value out across those cells. This is true for population. If you're using other kinds of data where an average or a mean might be more appropriate, you might actually just copy the value to every cell. So for example, if you were using temperature data here, you might just want everything that fit within a given polygon representing a temperature area, give it the same temperature, and you'd just be doing a copy operation. In this case, we're actually splitting it up, and you can get fancy here, which is actually something we've done for this particular data set, where in addition to just sort of splitting out the data across cells, ideally you want to split it out proportionally to how much of the polygon is contained by a given cell, and that gives you a pretty good representation of how much data might be in a given H3 cell once you've transformed from the polygons. So now we have this census data set, but what I really want to know is not just what does the census data look like and what does my crime data look like. I want to be able to join them together. I want to get normalized counts. So what I've done here is to take my crime data and take my census data and to stick them together. And you could do cell arithmetic, which you might be familiar with in the raster world. You call this raster arithmetic. In the grid world, you call it cell arithmetic, where you're just able to stick these things together and do calculations for the same cell across multiple data sets. In this case, all I'm doing is normalizing by population, and I got this different view of the data. So you can see if you sort of go between them, you can see that the non-normalized data shows a lot of incidents over here, sort of in the center of Oakland, and a lot of incidents down here in East Oakland, and a lot of incidents over here in downtown. When you normalize by population, well, you can see that the downtown actually comes out quite a bit because it has fewer people living there, but a lot more crime. You can also see some other patterns start to emerge. East Oakland is still looking a little bit higher for population. This central area, with the exception of this hotspot, looks like it's actually not too bad when you normalize by population. And you can also see some of the features that matter coming out here in your data set. So for example, here you can see some of the roads. I believe this is a freeway, this line that you can make out here. Obviously not very populated, but maybe a large source of criminal incidents. My guess is that many of those incidents would be vehicle incidents. They would be, drunk driving or things like that. Conversely, there might be people living under the freeway, and that might be a dangerous area. So this gives you a better sense of the kind of things kind of features you might find in your data. Another thing that's really useful to do with H3 in many cases is to do some kind of smoothing operation. And for example, if you're going to buy a house and you're looking to use this kind of data for site selection, you don't necessarily want to know, was there crime right in my little cell? You want to know, was there crime in my cell or in the neighboring cells, or maybe even the cells beyond that? So a smoothing operation is a way to take the effect of some data in one cell and spread it out to its neighbors in a way that allows you to get a better and more complete surface of how crime might look in a city. This was actually one of the key things that Uber used early on. I'm not sure this is going to endear you to Uber or to H3, but one of the first reasons why H3 was developed at Uber was to calculate surge. And the way that surge is calculated is to say, how many drivers are nearby and how many people asking for rides are nearby, and to then run an algorithm over that. In order to do that, we need to sort of spread out the demand and spread out the supply across the map, so you had these surfaces that you could stick together and then calculate surge based on whether or not you needed more drivers or fewer drivers. So being able to do this kind of operation allows you to create what I think of as a data surface that you can then use for other kinds of analysis. One other operation I wanted to show here, and this is something I also worked on a lot when I was at Uber, is clustering. So clustering is a way to create your own, if you will, your own admin boundaries. Early on, when I worked at Uber, we had this idea that we were going to create a system that would represent all the neighborhoods in a given city using hexagons. We thought this would be useful because then we would have these sets of hexagons that we could easily use for further analysis, and we could join with other systems and use as a canonical sets of area boundaries within a city. And one of the feedback we got on this idea was, why would you use neighborhoods? Neighborhoods are basically a real estate concept. In many cases, they're actually created by realtors. We were not a real estate company. We were a transportation company. So really what we wanted was a set of administrative boundaries that we define based on commonalities around transportation. Maybe we want one area where a lot of people request rides and another area where very few people request rides. So one way to do this is to run a clustering algorithm. It's really valuable in this kind of context to have a common unit of analysis, like a cell, that you can then treat equally for this kind of clustering. So the way we do this is you start off with as many clusters as you have cells. Every cell is its own little cluster. And then you run iteration over iteration. And every time you're trying to find two clusters that are the best match and then join them into one. So you're iteratively reducing the number of clusters in your data set until you have some desired threshold. So in this case, I think I set it to something like 20 clusters. And it just runs until it finds those 20 clusters in which things were the most like each other. Now, I have best in quotes here because best obviously is going to change radically depending on your use case. You might have, lots of reasons looking at the data that you might think that two cells are similar to each other. One potential way you could do this is something like vector similarity or another similarity analysis. But you also might have all these grid-based reasons why you would want to join cells. So you might care whether cells are adjacent. You might care whether cells and the clusters are more or less concave or convex. So you put all these different considerations into what's called an objective function, the thing you're trying to maximize, the thing you're trying to make every cluster best at. And then you keep on repeating, and eventually you have these clusters that provide some meaningful grouping of areas in your area of interest. And you can use these for further analysis. So a good example here that we did at Uber is we did a clustering algorithm which helped us to figure out what was sort of downtown versus outside of the core of a city versus suburbs, because these things had very different usage patterns and we could treat them differently. We could have different kinds of rules around what could happen there, and we could offer different pricing, et cetera, in those different areas. And we did this by building out this clustering system that could take all the hexagons within a given city, run it through some objective function, and create the areas that we really cared about for our business. So hopefully that gave you some taste of what you can do with H3. There's a lot more. This sort of generic grid gives you access to a whole bunch of really interesting kinds of algorithms, many of which you could do with traditional data. They would be slower, usually. They might be much more complicated to implement. And often they're just harder to think about. One of the things I really like about H3, and maybe this is me coming at it from a software engineer perspective rather than a GIS professional perspective, is that you're just dealing with these easy to visualize, easy to understand units. You don't have to worry about edge cases outside of the grid, because there aren't any. You're just dealing with the grid cells. And as I said at the beginning, you're dealing with a clean mathematical space that's much more amenable to different types of analysis, different types of algorithms, thinking through how to do different types of transformations. We've talked a little bit about spatial indexing. That's probably the most, straightforward use of H3, is simply to index your data and be able to pull it back up very quickly. Parallel processing is something that you can do in many different systems, using H3 as a way to shard your data, to break it up into different batches that you can then send to different servers or just different processes on your machine. This can make things very fast, where otherwise you'd have to do them one by one. Radius searches, raster conversion. We talked a little bit about suitability analysis. This is something where if anyone's ever done suitability analysis in a GIS system, it can be this long process of trying to get all your data into common formats where you can actually join it together. And sometimes you end up with weird slivers and other pieces that don't fit well into your analysis. Suitability analysis is a great example of where using a grid system allows you to bring all of your data into this one common format, stick it together, and then run whatever calculation you'd like to run across every cell. Similarity analysis is a little bit similar. You can do anomaly detection, forecasting. Flow analysis is really well suited for H3, because you can easily have data flowing between the different cells. And again, this is like only a short list of the kinds of things you might want to do here. So I want to do a quick call out for Studio. This is the application I work on in my day job. We use H3 a lot. It's not the only thing we use. You can think of it as a lightweight web-based mapping application, but it can create some highly interactive, really fast and beautiful maps. Everything I've shown you here today is something I created in Studio. It is not really a competitor for the hardcore GIS applications, but it's something that can be a really useful complement, I think. The one other thing I wanted to say as I wrap up here, here's a bunch of other ways to get in touch, a bunch of other ways to contact us. I put @ and Rabinowitz here because that's my handle on most platforms, including Twitter and GitHub and a few other places. But I love you to get in touch. And one of the things that I think we are weakest on in H3, H3 is a really good tool for software developers, and it tends to meet the needs of people building software, or in some cases doing data science around geographic data. It doesn't yet integrate as well as I'd like with traditional GIS systems, with ArcGIS or QGIS. You can work with H3 in those systems, but there aren't the kind of tight integrations that we have with, directly with Java or Python or some of the database systems that we work with. So I do want to end this with a call for help, a call for collaboration. If anyone is interested in pursuing that, I would love to see discrete global grids in general, but especially H3, obviously, get more adopted in the GIS community, because I think it's a really powerful tool for doing types of analysis that you might not easily be able to do using other tools. So thank you very much. I really appreciate your time. I hope you've learned a lot about hexagons and have something to tell your friends. And with that, I think we'll open it up for Q&A.
Thank you, Nick. This was extremely informative. I have to admit, I've learned more about hexagons than I've ever dreamed of, and I mean that
more than you wanted.
No, I mean it in a nice way. It is fascinating, because we're always, especially us geeks here in GIS, we think spatially. So this has been very, very helpful. In fact, one of I guess it's more of a comment than a question, but there was somebody who wrote in and basically said, gee, where were you when I was beginning my GIS studies? You had made this so easy to understand. Thank you.
I appreciate that. Thank you so much.
And a shout out to your Datamon as well in the beginning.
It really just cracks me up. I have to say it was so spot on.
Yeah, and this is a great group to do that with. It's safe with us. A question, and by the way, folks that are listening, please send us your questions. One question I have from Andy is, how is this different from the 3 words, the 3M grid system?
Yep. So that's a good question. That comes up a lot. I would say that what 3 words, as I understand it, and I'm not an expert in that system, but as I understand it, it's only covering a small portion of what a grid system like H3 covers. It's really only covering the unique identifier portion. And that's an important thing to cover. And I will say that, what 3 words, obviously it's easier to say 3 words. And this was, I think, part of the point. It's much easier to say 3 words than to say, where's my example index, but to say 85283, that's not a really human-friendly way of talking about a geographic area. But I don't think it provides the same kind of grid operations that H3 does, and it doesn't have the same concept of uniform area grid cells, to my knowledge. So I don't think it's solving all the same problems. I think it's solving a very small subset, and it solves that small subset, the unique identification, maybe a little bit better than H3. So if that's the only thing you're worried about is uniquely identifying an area and then being able to index that in multiple systems, then what 3 words might be a good choice, especially if you need to communicate this to people verbally. But if you want to do the types of analysis that I've shown here, I think that in general, H3 is going to be a better bet for the general purpose analysis use case.
Thank you. And Tony is asking, how much of a presence does R code have at H3?
That's a good question. There are some bindings for R. I think that the main one that gets used is it actually uses H3.js. So it's using the JavaScript bindings within R. And that's community maintained. So not something that I've worked directly on. I would love to see more adoption within R, because I think that data scientists in general, get a lot of value out of H3, and many people are using R as their main environment. But I think it's a little bit less. It's a little bit less supported, a little bit less well represented than, say, Python for some of the main use cases that we see. There definitely is some representation in the community, and I would love to see more work there.
Great, thank you. And I have a sort of a little question or challenge out to folks listening in. I would ask you guys to go ahead and type in the question area if you've used hex bins in any of the Esri tool sets to visualize and analyze your data, and what kind of projects were you working on. And while we're waiting for some of that to come in, I'll mention that I used it for some emergency services data, which started out as point data, but to visualize in hexagons. And I thought that was a really nice way to kind of spread that out and make it more visually, I think, visually understandable, instead of, as you were pointing out early on, a bunch of points, and it makes it look, I don't want to say messy, but a little bit less understandable, or misleading even.
Yeah, I mean, I think that one of the biggest issues you find with showing a lot of points, going back to this original point data set, is that you really can't tell where you have many points overlapped over each other versus a single point. So it's very hard to tell whether this area right in the middle of downtown has 2 points or 150 points or 1,000 points. If they're all happening in the same place, then they look exactly the same visually. So being able to bin, I think, is a really important step, no matter what binning system you use, if you want to understand the overall distribution of especially a large point data set.
Yeah. Anyone have any projects or thoughts on this they want to share? Got one here. Andy used hexagon coverage for some statistical analysis of wells, and he said hexagons provided a regular shape coverage with less variability occurring in the dimensions over a surface. So yeah, that's, I think, Great example. And I've seen it used here in my office. My coworkers have used it before. I think it's not only just visually appealing, as you pointed out earlier on, it has obviously some strong benefits.
And I think one of the things that we've tried to do at Unfolded and now at Foursquare. So Unfolded, I don't know if I explained this, but Unfolded was the startup I worked at doing this geographic visualization software. We were acquired this summer by Foursquare, and that actually unlocks a lot of things because Foursquare has a great number of data assets. They have these great data sets that are really one of their main things that they sell. And one of the things that we've been looking at, because H3 is this great general purpose grid, it allows you to put together these really big general purpose data sets that you can then deliver as needed. So the population data set, the census data set is a really good example here. You can create basically a population surface for the entire United States or even for the entire world, and then you can just deliver the bits you need to the people who are really interested in that. And they have this, this data set that's already set up for interoperability. If you want to join disparate data sets, things like population and weather and elevation and these things that might come, traditionally might come in very different formats, it makes it easy to just sort of stick them together, use them right away for analysis.
Nick, when we first talked to you, prior to today's presentation, you had mentioned that when you were at Uber, you ran into some, and you mentioned this, by the way, a little bit in your presentation today, but some jurisdictional challenges. So when you were trying to figure out SHRUG and how to model that, can you talk a little bit more about that and what you experienced with, especially with foreign countries and things like that?
Yeah. So, I mean, I think the main thing that we found in our early work on SHRUG, and I think you'll find this in a lot of cases, particularly where you have a mismatch between the geographic model that you're working with and the actual use case that you're working with. So we were working with, I think neighborhood boundaries or something like that and trying to calculate SHRG. And you ended up with all these weird edge effects where, you'd have these neighborhoods that were effectively very close together and we had drawn some line between them. And so you'd have high surge in one neighborhood, very low surge in the next neighborhood. And then you have lots of people who are trying to game the system in one way or another by crossing the line and getting low surge or crossing the line and getting high surge, depending on which side of the market you were on. And we had these problems that were essentially due to a mismatch between our geographic model, which was administrative boundaries, and our data model, which really didn't care about those boundaries at all and was much more about supply and demand as a surface across a given city. And so I think that one of the things that using H3 allowed was to ignore and basically distribute the effects of all those edges. We could make a much more fine-grained picture of supply and demand, and it wasn't at all bounded by essentially by the arbitrary, to us, nature of the administrative boundaries. Administrative boundaries are super interesting to me because they all encode history in different ways. They encode laws and legislation in different ways. And if those things matter to you, if you're really concerned about the particular history that created an administrative boundary or the particular differences between legislation on one side or the other, then the administrative boundary is super important. But if you're doing a weather analysis, the weather doesn't care about your administrative boundaries. It's going to, your hurricane is going to go right over the county line. It doesn't matter at all. And so using administrative boundaries to model this can actually be, a problem for your analysis because you get edge effects and boundary effects based on administrative boundaries that have no real bearing on your use case. Not sure if that's the question you were asking, but I think that was one of the main reasons why we originally developed H3 was to get around these boundary effects.
Yeah, and I can imagine how difficult it would have been to keep up with those neighborhood boundaries or those administrative boundaries. I mean, I know even just here in Tallahassee, the city limits are changing, you know, 4 or 5 times a year,
Yep.
albeit not terribly a lot, but you know, I would imagine these sort of things are going on all over the place. And how would you even keep up with that? I know
Right.
a
Whereas grid
homeowners
systems are
association stuff
stable.
here is, it's funny how they define an HOA, a homeowners association area. There's arguments you were talking about, you know, how you define those.
Yep. Yeah, the great thing about a grid system is that it's stable over time, as well as, you know, as within an analysis. You can refer to the same area of land no matter what period of, you know, of history you're talking about. It's the same grid cell in the, you know, Mesozoic era as it is now. Rather than, as you say, like admin boundaries are so changeable, and even on a yearly basis, let alone if you're doing some kind of historical analysis, it can be very difficult to get the right boundaries for the right area that you're working with.
Does anybody else have any questions they want to pose? All right. Well, I don't see any more questions. Let's see. I don't, Nick. Well, listen, I really want to thank you so much for your presentation. You had a lot of folks listening in, and I hope that our SHRUGgies got value out of it. I'm sure you did. Appreciate your contribution, Nick, and we wish you the best. And we look forward to maybe hearing from you again.
Well, thank you so much for having me. I really appreciate it. And please do reach out, especially if you'd like to collaborate, or just if you have any other questions. We're always happy to work with anyone who's interested in hexagons.
Thank you, Nick. Appreciate it. And again, this is being recorded, and we will put them out there in the coming days. So if you've missed anything, or you want to share this with someone that wasn't able to make it, we will be able to do so. Thanks again, Nick. Take care of yourself.
Take care. Thank you.